And we'll start from the current slide. Okay. One of these days the screen will come on. Okay, let me go over, went over with Jasmine last time. You'll get to hear it. If you listen to the YouTube video, you'll hear it again, but here's what's happening. Number one, have you done the student course evaluations?
No, I'm going to get it out of the way today.
Okay, good. Appreciate that. All right, and for everybody who's listening, please do the student course evaluations. Number two, by the way, what's next Tuesday? Not tomorrow, but a week from tomorrow. No, don't worry about that. Voting day. That's the special election for the Senate seat. Don't forget that. It has nothing to do with differential equations, but I just wanted to remind you, please vote. Okay? All right. That's so important. Okay? Decide. Okay. Now, let me go back and look. For this class, you have turned in your paper, and one other did too. One has not. The first test, two of you have turned in, but the third has not. The second test. What's that? Oh, you got your second test there. Okay. All right, here we go. First one in. Thank you. Okay. And I'll try to get these back to you next time if I can. Okay. Of course, I need to get the others in too. And then I'll have your third test ready for you next time. Okay. All right. And then you just need to get it back to me anytime during finals week. And let me just go over my schedule and stuff like this for this week, regular week. My office hours today are 3:15 to 5:15, same on Wednesday. On Tuesday and Thursday, 1:15 to 3:15. Okay. On Friday on the Birmingham campus, 7:45 to 11:45. Okay. During finals week, Monday of finals week, I have a review session with one of my classes. That will go from basically 8 to 10 in the morning on Monday morning. And then the rest of the day from 10 o'clock until 5:15, pretty much free. Now, if students come in to make up a final, and a few of them may be doing that, what I'll probably do is go to the classroom closest to my office and give them the final there. So if you're looking for me and I'm not in the office anytime during finals week, you can come up here and check first if you want to, check my office next, and then cover every classroom in between. I'll probably be in someone in between, okay? But on Monday, I'll be in this classroom 8 to 10. And after that, anywhere in between, if I'm not in the office. Okay, Tuesday, I have an 8 o'clock final. It goes 8 to 10. And then after that one, I have a class that starts at 3:15. It's a mini-term class, so it starts at 3:15. It probably won't go until 7:45, but that's when it's scheduled to go. Whenever we finish the last of everything we're going to cover, then I'll shut down. We do have a lab, I think, that day, so as soon as they finish with the lab, but I'll either be in my office, this room, or some room in between. So that's Tuesday. Wednesday, I'll probably be giving a final exam, and again, somewhere in between my room and this room, my office and this room, anytime, 8 o'clock in the morning, anytime during the day. It's a free-for-all day, and I will have some students, I think, coming in to take a final that day. Okay? Thursday, I should be through with my finals by then, except for people doing makeups and stuff, until the afternoon at 3:15, and then I've got one last final Thursday at 3:15. So anywhere Thursday morning from 7:45 in the morning until 3:15, probably be in any room between either my office or this room or any room in between, okay, giving finals. So look for me there. And then the final exam in that last class is not going to take very long, so I won't be up in this classroom very long that Thursday afternoon. So check for me in my office. Then Friday I'll be back on the Birmingham campus, so if you do need to get anything to me then, get it to me there. Grades are due, I think, by 12 noon either on Monday or Tuesday of the following week. I've got to check and see that, but I think it's Monday of the following week. So I'm going to try to have all mine in by before then. But if they give us until Tuesday, then may still be waiting for late papers or things like that. So, but they should be in. Now, I don't know if you're aware, but during finals week, you are not able to access Student Suite. You can access Blackboard, and anything that you've got in grades will be in Blackboard, but you won't be able to see Student Suite, which tells you your final grade, until after final exams are over with. The reason for that is, this is so bizarre, they only allow us something like 16 ports, you know, and if more than 16 students are inquiring about their grades on Student Suite, we can't get in Faculty Suite to put the grades in. And so they shut students out of it so we can get the grades put in. And then once all the grades are in, then they open it back up to students. So that's why. But everything will be on Blackboard. Or that's what I do anyway. Put it on Blackboard first and then put it there. All right. Now, any questions on differential equations before we get started? Okay, we're on chapter 4, which is higher order differential equations. 4.3, homogeneous linear equations with constant coefficients, and that's what we were doing. Example 1, we were on the C part of that, and that was this one. Let me get my pen set up. Now, I was just pointing out to Jasmine, I don't know, can you see that?
Yeah.
Okay, when I do this, then before this week, I could not pick that color because this was on top of it and it would turn it off.
Okay.
Starting today, it's not, so I can't pick that color. But before, when I was talking to Jasmine before, on the last one, it was over here, and I could still pick this. Now it's down here. So I don't know why it's moving around on me, but it's fine. But I don't know if you had noticed that, but I can pick black now. I think maybe I could in this class before. But anyway, here's solve the following differential equation. Y double prime plus 4y prime plus 7y is equal to 0. What's the technique? How do you proceed? I know it's been a whole weekend, but here's a hint. This is a linear, higher order differential equation, constant coefficients. Here is your answer. Let y equal e to the mx. Yes. Okay, where do we go from there?
You start taking the derivative.
Yes.
So it's m to the m. Yeah. Is it m to the m?
Okay, y prime is equal to.
Y prime is equal to m e to the m.
Right.
And then y double prime is going to equal to m squared e to the m.
Okay. Now plug in.
And then we plug it in and we get y double prime, which is m squared.
Yeah.
E to the mx plus 4 m e to the mx plus 7 times e to the mx
Is equal to?
is equal to 0.
0. Okay. And what can you do now?
You can pull out e to the mx.
Okay. E to the mx times
m squared plus 4m plus 7.
Okay. Now, here you have a factor. This times that is equal to 0. That means either this is 0 or that's 0. Is e to the mx ever equal to 0?
No.
No, never. It's always a positive number. Always a positive. It gets awfully close to 0 for very, very small negative m's, but it never is 0. So you can throw that one away, divide it out because it's not equal to 0, and then you're left with this one. And what can you do with that?
I think you remember. Either factor something?
Okay, if you could factor it, I would.
Yes, a quadratic
Formula, exactly. That one is not factorable because 7 is a prime number. No way you're going to get a 4 in the middle, so we go to the quadratic formula, which goes something like what? M is equal to?
minus 4 plus or minus square root of 4 squared.
Yep.
Plus.
No, minus.
Oh yeah, minus m squared times 7.
No. 4ac. B squared minus 4ac.
4ac, so
4
times m squared, I guess?
No. The coefficient.
Oh, 1.
1
Times 7.
times 7. Okay. Divided by?
2 times 1.
1. Okay. Exactly. So this is minus 4 plus or minus the square root of 16 minus 28 over 2, which is minus 4 plus or minus the square root of
15.
say again? 16 minus 28.
Oh.
Negative 12 over 2. But, number one, you can't take the square root of a negative number. Not in the real number system, but in imaginary or complex you can. That would be minus 4 plus or minus. Let's factor out a square root of negative 1. Right? Okay. That leaves us a 12.
Yes.
But 12 has the square root of 4 times the square root of 3. Right?
Yes.
Okay? All over 2. So it's minus 4. Yuck. Okay. Minus 4 plus or minus 2i, because I is square root of negative 1, right? 2 is square root of 4 times root 3, right? Over 2. Well, 2 will go into 4 twice, 2 will go into 2 once. So this is minus 2 plus or minus I root 3. Okay? There's what your M is. So this is either, all right, we'll just leave it like that for right now. All right, now, turn back one page, or you don't have your book with you, okay? If you have conjugate, and this is conjugate complex roots, plus or minus I times something. That's the conjugate pair, right? Then your M1 and M2 are complex. So let me write down what your M1 is. M1 is equal to minus 2 plus I root 3, and M2 is equal to minus 2 minus I root 3. Both of those are complex numbers, and they're complex conjugates of each other. Okay? Now, okay? And where you go from there, and this is what we did last time, basically, we rewrite, we think of this way, okay? Here are your solutions. Then y is equal to, I'm writing them down exactly the way they do it. And again, remember they use a capital C1, whereas all the other times they use a little c1. Okay? Don't sweat that. It's just how they write it. E to the, okay? Now we're going to go back to this form. I wish they'd sort of stick with one form or another, but this is what they get. Okay? E to the, and this is the generic form, alpha plus I beta x plus C2 e to the alpha minus I beta x. Okay. Oh, I'm sorry. Putting my parentheses in the wrong place. I knew something looked strange about that. Okay. Now there is your thing, but that has imaginary numbers in it and really messy, right? Okay. Now we're going to, and this is what we did last time. Remember Euler's formula and how we manipulate. I think we ran out of time before we were able to do all the calculations on it. But this is what your answer becomes. Okay? Whereas here, okay, here are your two solutions now. Okay? We're not going to use those capital C's anymore. Your y1 is going to be this. Okay? E to the alpha x. Okay? That looks pretty familiar, right? Times new coefficients, C1. They go through so many different forms. I'm trying to narrow it down to the final form. And it's at the top of page 137 in the blueprint. It's equation 8. Okay? It's okay. I'm sorry, I started to write it 1 and 2, but let's go back and put it to general form. Okay? E to the okay. I'm going to skip the intermediate. E to the alpha x times C1 cosine beta x plus C2 sine beta x. Okay. Okay. So basically you go from, and it could be this is a complex constant too. We don't want that. But we don't want i's up here. But these are the two. So what we do, you'll notice that e to the alpha x is in both of these. So factor that out. Okay? And then Euler's formula allows you to go from an I beta x to cosine beta x and sine beta x. These are not the same coefficients there. But this is what you get. That is your answer. even though you had imaginary roots here or complex roots here, your solutions have no complex numbers in them. These are just constants. These are just constants, you know. So this is the final form. All right, so let's take this final form and apply it to our answer here. Okay? Our answer here, our alpha is -2. You see it? The alpha is -2. So our final answer here is y is equal to e to the -2x. Okay? Times arbitrary coefficient C1 cosine. Okay? Your beta is your √3. Forget the I, it's just a √3. So that's going to be √3x. Sometimes I like to do x times √3 just so you won't think the x is under the radical, but I think it's probably better to write it this way here, plus C2 sine of √3x. So that's your answer for this case. So whenever you get a auxiliary equation that when you solve it, you get i's in it. In other words, your discriminant comes up negative. Okay? Then you go to this alternate format. And that's what it is. E to the, that doesn't have a constant with it, just e to the -2x times, and there's your constants there. Arbitrary constant, C1 cosine square root of 3x plus C2 sine square root of 3x. No i's in it anymore. Okay? And that's what you get. So the answer to C given here is y is equal to e to the -2x C1 cosine square root of 3x plus C2 sine square root of 3x. Now, be very careful when you're doing this. Don't extend that line too long and think it's the square root of 3x. It's not. It's the square root of 3 times x. That's why sometimes I like to put the x in front so you don't have that confusion. But I'm trying to write it the same way you both does it now. So that's how you do it when you have a complex, when you have, okay, this is your auxiliary equation. When you go to your, if you can factor, you just factor and go with it, okay? And you get them what the two m's are, and then you got it. If, however, that came up being a rational number, okay, that would mean, let's do three cases here. This is called the discriminant, the thing that's inside the radical, okay? If that came up positive, you have two real solutions, okay? It would be C1 e to the first one x plus C2 e to the second x. So whatever those solutions were to that, okay? If that thing comes up being 0, then you have, you would have this first thing that would be, in this case, that would have been a -2, e to the -2x, if that would have been a 0 here, e to the -2x plus x e to the -2x. You just put a constant x in front, not a constant, a single variable x in front, and that's if that was equal to 0. If that comes up negative, you put e to this thing in front, and then you have C1 cosine, whatever that came up being, the radical, if it was a radical, if it was a number, it's a number. Whatever the imaginary part, cosine of x plus C2 sine of x. Okay. So, let's look at an initial value problem, which then should solve your C's for you. You won't have any C's left in this one. So let me clear this. All right. Here's what we got. 4y double prime plus 4y prime plus 17y is equal to 0. But this time we're given the initial values. Y of 0 is equal to 1, no, negative 1. Why can it not write? Why is it? Okay, that's ugly. Okay. This ionizing pen sometimes is nice and sometimes really stinks. Okay. And Y prime of 0 is equal to 2. Okay. Now, time out again. If you have an initial value problem, if that's a nth order, you need n initial conditions. So this is a second order, you need 2 initial conditions. Usually Y and Y prime. Not Y double prime, that's too much. Okay, just Y and Y prime. If it was a third order, you need 3, usually Y double prime, Y prime, and Y. Okay, so yeah. So you usually go to 1 less than what your function was. Okay, but you need to. Where would you begin?
Saying that, well, Y is equal to, Y is equal to E to the MX.
E to the MX. Okay, and what would this give you?
Okay, well, I guess Y prime is ME to the MX. Y double prime equals to M squared E to the MX.
Perfect. So, yeah, plug it in.
So now we got 4 times M squared E to the MX plus 4 times M E to the MX.
I can't write. I'm trying to write an M and my pen keeps wanting to write a Y. Okay. Okay. Start over. Okay. M E to the MX
plus 17 E times E to the MX equals 0.
Okay.
And I get factor out of E to the MX. 4M squared plus 4M plus 17 equals 0.
See, the MX can't equal 0. So toss it. Okay.
Since that's not really factorable,
Yeah. Right.
So that's negative 4 plus or minus square root of 16 minus 4 times 4 or times 17. And then divide that by 2 times 4.
Right. Okay. So this will be minus 4 plus or minus the square root of 16. And this is going to be a minus. Doesn't look good, does it?
No.
What's 16 times 17?
272.
232?
270.
272. I thought that sounds better. Okay, 272 over 8. That would be minus 4 plus or minus the square root of
Negative 256.
negative 256
Yes, sir.
over 8, which will be minus 4 plus or minus 256 happens to be a perfect square, doesn't it?
I believe so. I think that's
16?
Yeah.
Is it?
Sure. Yeah.
Okay, so that would be,
I-16?
yeah, 16i. If it's not a square root, you can put the I at the back, okay? If it's a square root, I'll put it in front, over 8, okay? Which will be minus 1/2 plus or minus 2i, right?
Yeah.
Okay. Now, can you write down your solution then? Y is equal to?
Reduce very positive C1
Okay. Whoa, goodness gracious, where did that go? Okay. This is your alpha. That's your beta.
Yeah.
So e to the alpha x, which is e to the minus x over 2.
Yeah, then
Open parentheses.
Times C1.
C1.
And beta now, so it's 2i.
Cosine
Cosine. 2i.
to beta. You don't use the i's anymore.
Yeah, that's right.
Yeah. But yeah, that'll be x now. 2x. The beta was 2. I'm sorry.
Oh. Okay.
Yeah.
And now plus C1.
C2.
Oh, C2 times sine of 2. No, mine.
Nope, that's it.
That's it.
Yeah. Yeah. The plus or minus there just becomes sine and cosine there.
Oh, okay.
Okay, except we can now plug in y is equal to 0. So this is y at any x. So y at 0 would be, what's e to the 0? 1. Okay. C1 and cosine of negative 2. Right? No, I'm sorry. Cosine of 0. Sorry. I'm sorry. Plugging in the wrong thing. Okay.
Cosine of 1
Well, cosine of 0 is
1.
1. Oops. Lost my eraser. Okay. 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 Cosine of 0 is 1 plus 0. So y of 0 is C1 and C1, and y of 0 we also, wait. Okay. Is equal to negative 1. So C1 is negative 1. See, y of 0 is negative 1. Y of 0 is C1, C1 is negative 1. Okay? Okay, now let's go to our y prime. Okay, there's your y, so let's figure out what y prime is.
So it just be negative x.
Okay. Yeah, y prime is equal to, what do you say?
Negative x divided by 2.
Negative x divided by 2.
No, you're writing out the...
No, okay, that's your variable. This is okay. The derivative of an exponential is the exponential, remember?
Oh, okay, yeah, sorry.
E to the minus x over 2, but then you got a chain rule here, which would be a minus 1/2 in front. Remember? Okay. You got about 3 things going on here. First is the product rule. Okay?
Yeah.
So we're just going to do the first part of the product, which is the derivative of this.
Okay.
The derivative of this is itself times chain rule. Derivative of this would be minus 1/2. So that's where that came from.
Okay.
Okay. So that's the derivative of this, and that will be times the second, which is just this. Oh, and we already know what C1 is. It's a minus 1. So that's going to be a minus cosine 2x plus C2 sine 2x. Okay. Okay. Plus, okay, now the first times the derivative of the second, right?
Yes.
Okay, and the first is e to the minus x over 2, okay, times the derivative of this.
Which is positive sign.
Okay, of 2x
2 times 2, right?
2, yeah, times the 2 out front.
Plus 2, is that a 2 prime?
Yeah.
Okay. 2 cosine
2x. Okay. Now, I sort of botched something up there. Okay.
Well,
Yeah, no, we did right. That's a C2.
yeah, I thought we were going to put C2 in.
Yeah, I forgot. That's what I left out. But remember, yeah, because we already knew C1 was the -1. I thought I'd mess it up, but I got it in there. I forgot my C2 then because I took it out there. Okay, so this is what the first derivative is. Now we need to evaluate that at x equals 0. Okay? So y prime at 0 is going to be okay, no, it's negative. Okay, e to the 0 is 1, right?
Yes.
Okay, and you got a -1/2. Okay, so it's -1/2. Okay, that's what you were saying.
Yeah.
-1/2
Times. Oh man. -1.
Okay,
Plus 0.
plus 0. Okay, so that's just that.
And
Plus
1.
1 times
2. 4.
no, sine of 0 is
Sine of 0 is 0.
0. Okay, so that would be plus 2 C2.
Times.
This is it, isn't it?
Yeah.
Right?
Yeah.
Okay.
Yeah.
All right. Now, and we know this thing right here is 2. Okay, so we'll plug in 2 for that. I'm going to come down here and do it. 2 is equal to 1/2, because it was a -1/2 times -1. So that's 1/2 plus 2C2. Okay? Now, there's several ways you can proceed on this. How do you want to?
We can just start by doing.
What's that?
You said 1/2 minus 2.
Okay. Well, let's go the other way. 2 minus 1/2.
Okay.
That would be 3/2, right?
Yeah.
4/2 minus 1/2 is equal to 2C2. So C2 is equal to 3/4, right?
Yeah.
All right. So our answer is y is equal to e to the minus x over 2 times negative cosine 2x plus 3/4 sine of 2x. Got it?
Yes.
Okay, let's see if that's what they got. Y is equal to e to the minus x over 2 times minus cosine 2x plus 3/4 sine 2x. Ha! Good for them. All right. Now, they do show a graph. I don't think you got your text. This happens to be, is this the solution for that curve there? This one right here is, notice this is an exponential decay, right? So you have something that's big out here getting smaller in here,
Okay.
and this is a sum of two, trig functions, so that's going to be periodic in there. So this is how it looks, kind of. Okay, see, you have the envelopes coming like this. I don't know if you remember that. This is called why can't I think of the word? Damped trigonometric function. Remember that? The damping factor. This is the damping factor. E to the minus x over 2 goes out like that or like that, and then the trig function in between, it goes back and forth and it dampens out real quickly. So that's what this one looks like. Okay. Now, they do have a little blurb here on 2 equations worth knowing. So if they're worth knowing, let's know them. Okay. This is the button I wanted to hit. Okay. Erase all that. 2 differential equations. Here's one. Y double prime plus k squared y is equal to 0. Okay? Here's another one. Y double prime minus k squared y is equal to 0. Okay? Now, you can do your auxiliary equation if you wanted to. Okay? And if you did, that was going to come up m squared plus k squared is equal to 0. Right? If you had gone through all your fiddling with it, right? Well, I hope that indicates to you, certainly you can't factor that, and this would be m squared is equal to minus k squared, which of course you can't do. That would be m is equal to plus or minus ki. Okay? Okay? Now, if you did what we did before, notice your alpha is 0. So you have y is equal to, you don't have e to the alpha x. That would just be a 1. And you come up with cosine kx, or c1 cosine kx plus c2 sine kx. But you know, you knew that anyway, didn't you? Because if you take the derivative of this, you get minus k times c1k sine kx plus c2k cosine kx. And take the second derivative, and that would give you minus c1 k squared cosine kx minus c2 k squared sine 2x, and that is exactly what we've got here. You know, you got y double prime is equal to k squared times y. Okay, you just multiply this. Okay, so yeah, that gives you that one because the sines and cosines alternate, you know, signs back and forth, you know, in a pattern, and you wind up with the same thing you got. Now that one over there, that just gives you your auxiliary equation is m squared minus k squared is equal to 0. And we know what that is. M plus k times m minus k equals 0, right? We can factor that one if I can get it. So this is m is equal to k, and m is equal, or minus, goodness gracious, this is aggravating. M equal minus k, m equal k. Okay, so then we have y is equal to c1 e to the kx plus, or minus kx plus c2 e to the kx. Okay? And sure enough, if you take the derivative of this, you get minus c1k e to the x, and this will give you plus c2k e to the x. And take the next derivative, and you get plus c C1k squared e to the x, and you again get plus C2k squared e to the x. And yeah, if you plug that in, you'll see everything goes. So those are the two, because you see e to the kx, or actually the minus kx, alternates back and forth, sort of like sine, but sine and cosine do it in a pattern of 4, that does it in a pattern of 2. So you wind up with the same thing you had. And those are two really important ones to keep in mind. Now, this form here basically is that hyperbolic sine and cosine, right?
Yeah.
And for the life of me, why mess with a hyperbolic? Leave it just like that. That is so much easier to work with than a hyperbolic. But math books love to go to the hyperbolics. So you can if you want to, and that would be, an alternate form of that would be C1 hyperbolic cosine kx plus C2 hyperbolic sine kx, which is a real pain in the neck to use. But you can do it if you want to. Now, when you get higher order equations, in other words, you have nth order differential equations, in other words, the nth derivative, then you'll get m to the n, m to the n minus 1, m to the n minus 2, you get a polynomial, yay long. And then you got to see if you can come up with factors of it. But remember back in pre-calculus algebra where you used to use things like rational zeros test and Descartes' rule of signs and all those other really fun things you and love so well. That's what you do trying to solve those. So let's see if we can, sorry. Let's see, there were a couple of other things they wanted to say here. All right. If your auxiliary equation with your m's in it, if you came up with a repeated root for m, like m's equal to, hey, if you had, like this had m is equal to plus or minus ki, this is m equal plus k or minus k. What if you had m is equal to 3, 7, and 5? Well, then you'd have C1 e to the 3x, C2 e to the, like this. But what if you had a repeated root? C2 e to the 3, and then another C2. Well, then the second e to the 3, you put an x in front of it. X e to the 3.
Oh, yeah.
Okay, remember?
Yeah.
And if you had repeated root n times, then you have x to the n. Yeah, you have C1 e to the kx plus C2 x e to the kx plus C3 x to squared e to the k. You just keep adding another until you use up all those repeated roots. Okay. Now, remember in those polynomial equations like that, you can always come up with equations of the work, but if you have any conjugate pairs, they're always in pairs. So again, you always have your cosine and sine, so that's going to happen there. So hopefully that's covering all the bases here. Let's do a third order differential equation. Do we have time?
Not really.
No, not really. Yuck! That was so much fun. All right, we'll begin next time with example 3. Okay? Homework exercises here. Do any of the odds 1 through 13. any of the odds 15 to 27, any of the odds 29 to 35, and any of the odds either 37 or 39 or both. Okay, do 41. Do any of the odds 43 to 47. Okay, 49 through 57 are sort of interesting. We haven't done one like those, but, oh wait, no, I think we jumped too far ahead. Oh, sorry, wait, back up. Let me start over. Any of the odds 1 through 13, stop right there. We haven't done the 15. I was going to say, how are we getting all that far? Okay, we'll stop right there at 13, and then once we do the next 3 examples, we can do the rest of them. All right, good deal. All right. Sorry we got short-sheeted today on this one.